All right, kind people, we'll get started in a second. Oh, we're doing this today. Thank you. Oh, okay. All right. Good afternoon, kind peoples. How are we doing today? All right. So I only have one announcement, and that announcement in the original syllabus, the test on chapter 4 was scheduled for Monday, but we found out a few days ago that Monday is now a holiday. Yes. This is actually a one-time holiday because of the 250th anniversary of the nation. And so Monday, the test is going to be moved to Wednesday. All right. All right, so that's the only announcement. All right, so we will get started. Last time we did the addition rule for probability. Remember, in 4.2, we're moving into the more complex space. And in that space, what's going to be happening is we're doing the probability of more than one thing happening at the same time. Yes? And as you'll learn a little bit later, there are basically two ways that can happen. Is either we're considering one or the other happening, or them happening at the same time. Yes? Right? And so what we're going to go through right here is go through how we do those calculations. And the first thing we looked at was the addition property right here. The keyword for addition is or. And when we have or, there are actually two formulas to find the probability. Yes? This first one called the generalized probability rule, where the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Yes, that's the first rule right here. The second rule is in a specific circumstance when you have two events that are mutually exclusive. Anybody remembers what it means to be mutually exclusive? They cannot happen at the same time, right? And because they cannot happen at the same time, this probability is going to be zero. The probability of A and B happening is going to be zero because they cannot happen at the same time, yes? And when that happens, the formula simplifies. It simplifies into what we love so much, and that one is simply the probability of A plus the probability of B. Questions there? And then we try to do 500 examples, right, of them right here to go ahead and practice the two. One when they're mutually exclusive and one when they're not. Yes? All right, so we're moving on. We're continuing in 4.2. And let me find, let me find that for me right here. So we're continuing 4.2, the addition and multiplication rules. We're going to be moving into the multiplication rules today. I'm not sure, 100% sure if I'll get to conditional probability. If not today, I'll get to it on Wednesday. I'm actually hoping to have everything wrapped up by Wednesday, but we'll see. Either way, I'll get it done. All right. So when two events occur at the same time, we use the word and. Okay, when two events occur at the same time, we use the word and. Okay, what's the probability that the Seahawks win the Super Bowl and get an interception? Yes, the two things have to happen at the same time. Not simply that they win the Super Bowl or that they get an interception. Both things are occurring in the same time space, in the same event. Yes, that's why I'm going to use the word and right here. And the key thing, right, one of the key things right here is we have to learn about what's called independent events. Anybody happens to know what two independent events are? In the local colloquium, when we say events are independent, it means one does not affect the other. Yes? Like, for example, whether or not you arrive, not a good example. That's actually dependent events. Like for example, whether or not you arrive to class on time and the chemistry building is open, right? Those things have nothing to do with each other, right? And so these events are independent. In other words, there is no way that the two events are linked together. Questions there. Unlike, for example, the probability that a team wins a football team and if they get a turnover. Yes? Those two things are actually highly correlated, are highly linked together. If a team gets a turnover, they're a lot more likely to win the football game. Yes? And those are what we call dependent events. Again, events that are linked or correlated one with another. Questions there? So here's the thing. When two events are independent, the probability simplifies. The probability of the two things happening is simply the product of each probability. Okay? Two things are independent. The probability is just multiply them together. The classic example is if I'm going to spin a coin and roll a die. Spinning the coin will not affect the die, correct? Rolling the die will not affect the coin, yes? And so if I ask, what's the probability of me getting a heads and then getting a 7 and getting a 4, I just multiply the two probabilities together. And that'll give me the probability of getting a heads and a 4. Okay? So, and so the probability of getting heads is going to be 1/2. The probability of getting a 4 when you roll the dice is going to be 1 out of 6. So the probability of heads and of 4 is going to be 1/2 multiplied by 1/6. It's going to be 1/12. Oh, nothing's in the way, huh? Go away. There you go. And so the probability of getting a heads is 1/2. The probability of 4 is 1 out of 6. The probability of getting heads and a 4 is going to be 1 out of 12. Questions there? Questions there? I can actually show this to you pictorially. I need to close this and then put it back up again. So this is the sample space. In the sample space right here, a person can either get a heads or a tails, and they can either roll a 1, 2, 3, 4, 5, or a 6. Yes? One possibility is I get heads and I get a 1. Another is heads and I roll a 2. Another is heads and I roll a 3. Another is heads and I roll a 4. Heads 5, heads 6. Then tails 1, tails 2, tails 3, tails 4, 5, and 6. These are the only possible outcomes. This is my sample space. Yes? How many items are in the sample space? 12. How many of these items are I get a heads and I get a 4? How many times does that happen? Once. So therefore, the probability of getting heads and the 4 is going to be 1 out of 12. All right? And that's why the answer works to multiply them together when they're independent. Questions there? Comments, queries, concerns? All right, cool. So that's our lovely formula. Just multiply them together. Let's look at some examples. You draw one card from a 50 card deck, then the card is replaced, and then the deck is shuffled, and you draw again. Find the probability of getting a king each time. Before we can try to solve this problem, we have to ask ourselves, is these events independent? Is drawing a king from this deck is it independent? And the answer is going to be yes. Because the first time I'm selecting how many kings can I choose? There are 4 kings out of the 52 cards in the deck, yes? I pull a card, I put it back in, I shuffle the deck. How many kings are in the deck? And so it's the same 4 out of 52 chance, yes? And so the probability of getting a king does not change. And so therefore, the probability of getting 2 kings is simply going to mean the probability of getting a king on the first pull multiplied by the probability of getting king on the second pull. Questions there? And so that's going to be 1 out of 13 multiplied by 1 out of 13, which gives us an answer of 1 out of 69. There's a 1 out of 169 chance of getting a king. In Texas Hold'em, there's this thing called pocket rockets. You ever heard that before? When you have you pull 2 aces, yes, you have a 1 in 69 chance of pulling 2 aces. Yeah. No, really? It happened to me once, so I'm waiting for my 169 times to come around again. Anywho, I'm paused. Questions there? The key thing right here is that the probability of getting a king and the probability of getting a king right here, those probabilities do not change. Whenever that happens, the events are independent. If one happens, it does not change the probability of the other thing happening. All right? On the other hand, let's say you draw one card from a 52 card deck, then it's the same. Oh, it went backwards. About the same. That don't look like the question I'm looking for. Where's my question I'm looking for? Where is it? There we go. Dependent. Where did it go? There we go. On the other hand, let's say you have the same 52 card decks right here, but this time you do not replace the king. You do not replace the king. Yes? So I pull out one card, I put that card down, and then I go again, I pull out a second card, and I put that card down right here. So on the first attempt, what's the probability of pulling a king? It's going to be 4 out of 52, yes? Let's say I get a king. Let's say the first card is a king. What's the probability of getting a king the second time? So probability of getting a king right here is going to be, I forgot what it was, 4 out of 52. Now that I checked, it is a king. What's the probability of getting a second king? It's going to be 3 out of 51, yeah? Right? Because one card has left the deck, yes? Did the probability of getting a king change? It did, yes? And so because of that, we say that these two events are dependent. These two events are dependent. One affects the other. Notice, very importantly, that the number of cards in the deck has changed. Yes? Let's say we rerun the experiment. The second time we run the experiment, we don't get a king. So I pull a card, I look at the card, and that card is not a king. What's the probability of getting a king the second time around? It's going to be 4 out of 51. Did the probability of getting a king stay the same? No. And so the point is, it doesn't matter what happens, these two events are dependent on each other. Okay? Questions there? Questions there? All right. Interestingly enough, where is my done button right here? Define the probability of getting a king on the first vote is going to be 1 out of 13. And then the probability, assuming we get a king, then the probability is going to be 3 out of 51. And again, these are two events happening one to each other. You simply multiply them together. So the probability of getting two kings is going to be even worse. It's going to be 1 out of 221. Actually, I was wrong in the pocket rockets. This is actually the probability of picking two aces because you have to have both. Oh, I was wrong. And so it's even worse. I with my 221 deals. I go play me some Texas Hold'em. And the interesting thing though is that the one time I got, I still lost, and I had two aces. But anyways, that's going to be a probability right here. Notice, again, we have an event and two events happening. We're still multiplying the probabilities together. The difference is the second probability is harder to calculate because we have to adjust for what has happened from the first item. Questions there? Comments? Queries? Concerns? And means to multiply, or means to add, or add and subtract what they have in common. If the two events are, how should I say it? Not mutually exclusive. All right, so let's look at some more examples. Find the probability of a baby girl being born. Oh, the probability of a baby girl being born is 1/2. Find the probability of 7 girls being born in a row. Question, are the events of having a baby girl, are they dependent or independent? If you already have 3 girls in your family, does it change the probability that the next child is going to be a girl? It's not. It's independent, yes? And so the probability of having a family of 7 children, and all of them girls, is going to be multiplying each of the events together. 1/2 7 times, or 1/2 to the 7th power. And that's going to be a decimal of 100. Well, I was going to keep it a decimal, sorry. 128 divided by 1. Where is my calculator when I need it? 1 divided by 128 is 0.007812. So you have less than a 1% chance of having a family of all 7 girls. Questions there? 1 out of 128 chance of that happening. Questions there? All right, another example. If the probability of being hospitalized during a year is 0.35, find the probability that no one in a family of 8 will be hospitalized that year. Round your answer to 5 decimal places. Oh my goodness. Questions. Are these events dependent or independent? How many people are in the family? 8 people. Is this independent or dependent? Now, I'm just going to tell you this right. It's part of us growing up as statisticians. In this question, it's set up to be independent, right? But they're really true. If the people are all from the same family, they may have, for example, similar genetics. Yes, they live in close quarters. For example, if they have a virus going around that tends to hospitalize people, one person gets it, there's a high probability that someone else will also get hospitalized as well. Yes, right? And so, as a statistician, you can start seeing that sometimes these things are difficult to calculate because sometimes we have what's called a hidden connection that is not obvious to us. Yeah. But in this example, they want us to look at it as face value. And so they want us to treat them as independent events. Yes? In other words, someone driving a car, they get in an accident, they go to the hospital. that's not going to affect other family members going to the hospital. All right. So, question right here is that we have a problem. The probability of being hospitalized is 0.35, yes? But did they ask what's the probability that did they ask what's the probability that the 8 people will be hospitalized? Is that what they asked? They asked what's the probability that no one will be hospitalized, yeah? And it's a classic trick that the test writers like to use. They like to give you information in the positive and ask you about the negative. Yes? So what's the probability that a person is not hospitalized? 0.65. Does that make sense right here? The probability of not being hospitalized is 0.65. Does that make sense to you? Because it's the opposite. It's the complement of the set. Yes? No? Maybe? And so this is the actual number that we need. So that's what you see they do right here. First, they find the complement of the set, 0.65, and then you just multiply 0.65 times by itself right here. So I have how many people in my family? I have 8 people. What's the probability that the first person does not get hospitalized? 0.65. What's the probability that the second person does not get hospitalized? 0.65. What's the probability of the third person, and the fourth, and the fifth, and the sixth, and the seventh, and the eighth? Hey, aren't you glad you get these calculators? No? Aren't you glad you get these? No? And so that's going to be 0.65 to the 8th power, and that's going to be 0.0318. There is only a 3% chance that nobody gets hospitalized. Someone's going to the hospital. Is it you? Really? Yeah, the real issue right here is this number is incorrect. Most likely the probability of being hospitalized is much lower. Because the answer right here, again, interpreting the results, they're saying that there's a 3% chance that no one goes to the hospital. In other words, there's a 97% chance that at least one person will go to the hospital. Yeah. But from our living experience, we know that that can't be right. Yeah. In a given year, how many people in our family go to the hospital? Not a lot, right? Right. And so from our given experience, we can estimate that that number is incorrect. Questions there? Again, that's us growing as statisticians, not just simply looking at numbers and saying it must be true, but thinking about the process that's going on behind it. All right? Questions there? Also, another key factor right here is that it is a large family. The more people in the family, the more likely someone will be hospitalized. Yes? Yes? If you have a family of 500 people living under one roof, somebody's gonna go to the hospital. You have to have a big apartment, but like 100 floors. Yeah. You guys don't live in those bigger, no. All right, at least one. I already talked about at least one. Let's remind ourselves again. There are 6 multiple choice questions on an exam, each with 5 possible answers. Oh my goodness. If you are guessing, what is the probability of getting at least one question correct? So again, the way we're going to do this right here is we're going to find the probability of getting none of them correct and then just flipping the answer. Yes? If the probability of getting none of them correct is 10%, then the probability of getting at least one is going to be 90%. Yes? That's what we're going to do. All right, so let's roll. So again, like I said, the first thing we're going to do right here is find the probability. Actually, they're doing slightly differently right here. First and foremost, how many choices do we have on a question? 5 possible answers. And so if I'm guessing, what's the probability I get the answer wrong? That's going to be 4 out of 5. Yes? Yes, if I'm guessing, it's going to be 4. By the way, that's actually one of the ways you can tell the difficulty setting on a test. In the SATs, you had 4 answer choices. On a lot more of the higher advanced exams, like to become an accountant or whatever, they go up to 5 questions. That small change makes a huge difference in the probability of guessing and guessing right. Anywho, so a 4 out of 5, that's the chance of getting the question wrong. So at least one answer correct is 1 minus none of them correct. Can somebody guess or make a stab at how do I find the probability that none of them are correct? Anybody can make a guess at that. How do I find the probability that I get none of them correct? I don't need the answer. I just need what to do. Anybody? Don't you all raise your hand at the same time? Okay, if you raise your hand, I'll help.
When you said to find how to get none of them correct, you have to find at least one.
No, it's going to be simpler than that. On the first question, will I get the first question right? So the probability of that is
4 out of 5.
4 out of 5. I move to the second question. What's the probability I get the second question wrong? 4 out of 5. I move to the next question. 6 questions in all. Each of them is going to be
So you multiply.
yes. So I got the first one wrong. I have got all 6 of them wrong. Yes. The probability of that happening is 4 out of 5 times 4 out of 5 times 4 out of 5 times 4 out of 5 times. Yes. Does that make sense? That's the probability of me getting none of them wrong. So in other words, the probability that I get none of the questions correct is I get the first one wrong, the second one wrong, the third one wrong, and so forth and so on. And that's going to be multiplication. 4 out of 5 times 4 out of 5 times 4 out of 5 times 4 out of 5, 6 times, yes? And so let me hide this piece right here. 4 out of 5 raised to the 6th power is the probability that I get no question correct. Does that make sense? If you want to raise your hand, go ahead and raise your hand now. Okay, if you want to raise your hand, go ahead and raise your hand now. All right, if you want to raise your hand, go ahead and raise your hand. Yeah. Yes. So the question is, do you understand why? Go back. Do you understand why it is 4 out of 5 raised to the 6th power? That's my question right here. Do you understand why 4 out of 5 raised to the 6th power is the probability that you got every question wrong?
Is it yes or no question?
No, it's not.
Is it because you have to like every?
How many questions are there? 6 of them. What's the probability of getting a question wrong? 4 out of 5, yes? So there are 6 of them, so it's 4 out of 5 to the 6th power. All right? Now, why am I subtracting from 1? Why am I going 1 minus I got none of them correct? Because when I do that, that'll give me the probability of at least one of them being correct. Yes? And so therefore, when you're handing down the calculator, it says you have a 73.78 chance of getting at least one question correct. Yes.
So if it was like at least 2, you can do 2 minus.
You would have to find the probability of getting none of them correct and the probability of getting one of them correct, and then subtracting that from 1. Subtract both of them from 1. All right? Anybody else? Anybody else? Anybody else? So a lot of people are misleaded by this right here. So does this say I should guess on the test? Does it say I should guess on the test? Look, there's a 74% chance that I get at least one question right. Should I guess on the test? No, of course not. Right? Because there are what 6 questions, and it says if I get one question right, I didn't pass, right? Right? This is at least one correct. It's not saying I get 5 of them correct. Yes? Questions there? So yes, no, you should guess on the test. I digress. Questions there? All right, cool. See, I had a little picture right here if someone raised their hand, but nobody raised their hand. I had a picture. All right. That moves us into the last piece of this section. How much time am I doing? I got 5 minutes. And that takes us to something called conditional probability. A conditional probability It's like we saw at the king a while ago, when that we already know something has happened. The classic example is the one that they have right here. The probability that an adult male is above 6 feet tall is 15%, right? So there aren't that many people around that are taller than 6 feet tall. Yes, higher than 6 feet tall. Yes, but if I said the person I am thinking about is someone who plays in the NBA, is the probability still going to be 15%? The answer is no, it is not. Yes, right? I'm saying, hey, the person I was talking about is a basketball player. That probability will change. That new probability is called a conditional probability. The probability of the event happening is based on something that has already happened or something that is given. Yes? A classic example, your deck of cards. I have pulled one card from the deck and that is the king. What's the probability that the next card is the king? That probability is going to be dependent on this card. Yes? Yes? If I pull a king already, it's going to be 3 out of 51. Questions there? All right, so we have some notation. Like I said already, the probability is going to be much higher. Actually, the probability that an NBA player is greater than 6 feet tall, I think the answer is like 97% or something like that. Almost everybody in NBA is taller than 6 feet. Yes, so it changes quite drastically when you pay people to be tall. Yes, I wish I knew how to do that. Pay my children to be tall. All right, conditional probability right here. Conditional probabilities right here. If event B is dependent on event A, we can write this out right here. We can write the probability of B given A. This right here is saying what's the probability of an event given that an event has already occurred or that we know something to be true about the scenario. Okay, the classic example is what's the probability of pulling a king given that the card I pulled the first time is already a king? That probability is going to be 3 out of 51. Make sense? This is the event that has already occurred. This is the probability I'm asking you to find. I'm literally asking, hey, what's the probability of pulling a king? But then I'm giving you more information. All right? The other example right here is what's the probability of pulling a king given that the first card was not a king? And that probability is not going to be the same. Yes? What's the probability of pulling a king the second time if the first card was a 2 of hearts? What's the probability of pulling a king the second time? It's going to be 4 out of 51. Yes? The more information I give you, the more the probability will change. All right? If I tell you, hey, I've pulled 20 cards from the deck, none of them are kings. What's the probability of a king the next time? It's going to be 4 out of 32. Yes? If I told you I pulled 50, not 50, I pulled 48 cards from the deck. None of them are kings. What's the probability the next card is the king? It's going to be 100%. Yes? Right? Pulled all the other cards, 4 cards remain. I haven't gotten a king yet. Then the next card must be a king. It's going to be 100%, 4 out of 4. Yes? Questions there? So the first piece is the probability I'm asking you to find. This is the extra information. And that extra info changes the probability. Well, not always, but it can change the probability. We say it reduces the probability space. Questions there? The classic example in drawing balls from a bag. The other class, we're catching up to them. I guess they teach this class right before us, right here. If A and B are dependent, then the probability of A is not going to be the probability of A given B. If the probability if A and B are dependent, by definition, if B occurs, the probability of A will change. two events are dependent, they're linked together. One occurs, the other probability will change. If they're independent, oh, sorry, got this one first. If A and B are dependent, and to find the probability of A and B happening, we still multiply. The difference is we first find the probability of A, and then we do not take the probability of B, we take the probability of B with the extra info. Let me say that again. I want to find probability of two things happening. Probability I draw a king, and then probability I draw another king. That's what I want to know. Yes? Probability of drawing a king is going to be 4 out of 52, yes? But I tell you, hey, this first card is a king, i.e., I am giving you extra information. Then the probability of drawing the second king is not going to be the same. It's going to be 3 out of 52. Questions there? Yes. Yes. All right, so let's see an example. I think that's what you're saying out loud. I guess I'll put this up right here. The formula also works backwards. They should actually have written this right here. The probability of B and A. They should have written it backwards. I don't know why they didn't. But if it was because and two things happening, doesn't matter which order they're happening. They happen at the same time. So it doesn't matter. Yes.
So when you're like on the just like you were saying like, oh, the first card is a king and the second card, but you still have the probability of 3/51.
Mhm.
51 because
There were 52 cards. One card is missing. So it drops from 52 to 51.
and then it's still like for P for the probability of being
B given A. The slash means the word given. Uh-huh.
that probability wouldn't change to like 3/51.
Yes, that probability is the 3 over 51. Yeah.
Oh, that's my question, because you said 3/52.
Oh, my bad. Yeah, 3 over 51. Uh-oh, almost out of time. All right, so let's look at a few examples and then we'll move on from there. I already did this example. Why did they call me in? I already did this example, so let's do the classic example. Not this classic example. All right, let's do a classic example right here. So let's say I have a bag, a very beautiful bag, and inside this bag there are 3 red balls, there are 3 green balls, and there are 4 blue balls. If you stick your hand, you pull it out, you put the ball down, and then you go ahead and pull 2 balls right here. What's the probability of selecting a blue ball on the first try? Let's just go right here. What's the probability of selecting a blue ball? There are 10 of them in all. 4 out of 10. What's the probability of selecting a blue ball? It's going to be 4 out of 10. Now let's say I pull 2 balls out of there. What's the probability of selecting a blue ball given that the first ball was red? What's the probability I select 2 balls? The second ball is what I'm concerned about. What's the probability of selecting a blue ball given that the first ball was red? It's going to be 4 out of 9.
Wait, but if I say you do two,
Yes. When I picked the first ball, right, it was red. Yes. Now I'm selecting the second ball. What's the chance of it being blue? Right? Not the third pull, not the third pull, the second pull. All right. All right. We're on the same page now. All right. What's the probability of selecting a blue ball given that the first ball is blue? It's going to be 3 out of 9. Questions there? The probability of selecting a blue ball is dependent on what happened the first time. Questions there? Questions there? Huh? Good. So let's try again. Where's my eraser button when I need it? What's the probability of selecting a blue ball on the third try, given that the first ball was red and the second ball was blue? So now I'm selecting 3 balls. I went in there, I got a red ball. I went in there again, I got a blue ball. What's the probability I get a blue ball now? It's going to be 3 out of 8. Questions there? Now let's switch the scenario around altogether. In this new scenario, I'm going to select the ball. I'm going to look at the ball. I'm going to put back into the basket. I'm going to shake it up, and I'm going to select the ball the second time. Right? This is called with replacement. So in other words, I'm removing this part of the problem right here. And I'm selecting balls, by the way, from the bag. Right? And so, what's the probability of selecting a blue ball in that scenario on my first pull? I'm going to select and put it back in. What's the probability of getting a blue ball? It's still 4 out of 10, yeah? What's the probability of getting first a red ball, then a blue ball on my third try? What's the probability of selecting a blue ball?
You're still replacing.
Yes, I'm replacing. Remember, I removed this right here. Whenever I select a ball, I put it back in the bag.
those sort of-
It's going to be 4 out of 10. What's the probability of selecting a blue ball if the first pool was green, then the next pool was blue, and the next pool was red? What's the probability of selecting a blue ball? It's still going to be 4 out of, because there are always 10 balls in the bag, right? Right? I'm putting it back in, so there are always 10 balls in there, yeah? And so therefore the chance of me getting a blue ball is going to be 4 out of 10. Yes? Yes? Whenever we have this situation right here where the probability does not change, or these things right here are not changing the probability, we say these events are independent. The probability is not affected by other events. Questions there? Comments, queries, concerns? We're going to stop right here and pause. Comments, questions, or concerns? Again, the thing to remember is whenever you say without replacement, when this is here right here, it's dependent event. When there is replacement, then the events are independent. All right. So what we're going to do for our last like 10 minutes or so is I'm going to let you guys finish the assignment. Hopefully you guys already finished it already. If you go into Canvas,